if more people filter in, they will filter in slowly. I don't have any huge announcements today. Just a reminder that if you're attending, the Dash meeting is in a little over a month, so keep that in mind. And then the PyHC fall meeting officially got announced, what, a week or two ago or something like that. There's a web page now up for it. You can find it via the normal way you would go to any of our other community-related meetings. But yeah, please go ahead and register for that and hope to see you there. It's going to be hybrid, so you can come online as usual or in person here at LASP in Boulder. And I think that's all that I have. Sean, do you have any big overall announcements?
Let's see here. I will, because you mentioned it, I'll go ahead and paste a link to the fall meeting website in the chat here. So
Thank
everyone
you.
go check that out, and the registration link is at the top. And I don't want to steal your thunder. Julie, you said you had no major announcements, but I think you do have one announcement, and I didn't buy
What I
it.
forget.
You got married.
Oh, yeah, that did happen.
What am I talking about?
I did. I was like, what else is there for PyHC? Yes,
So
thank you.
congratulations on that. I think that's good news.
Thank you. Thank you.
But other than that, no, I do not have any other PyHC things to mention this morning.
Okay. Sounds good. Thanks again. Great. Well, moving back into PyHC world, as you probably saw from the email reminder, we have Dan Brandt here today, and he's going to be speaking on executable irradiance models within PyHC. So by all means, the floor is yours.
Thank you very much, Julie. Thank you very much, Sean. So first of all, I just wanted to thank everybody in the PyHC collaboration for being willing to listen to me today. This is my first time giving a talk to this webinar. So I'm really excited to just like meet more people and talk about some of the stuff that we're doing. Also, I want to thank Aaron Ridley, who unfortunately couldn't be here today because he's like knee deep in proposal land. He's really like the driving factor behind this project that we're going to be presenting. And I really just kind of hopped on to help try to carry it through to completion in support of one of his major projects to develop a new ionosphere thermosphere model that he calls Aether. So without further ado, I believe I'm able to share my screen. So I will do that and we'll get started. So hopefully everyone can see that.
Sure can.
Great. So today I'll be discussing EUVPy, which is a new Python package that myself and Aaron Ridley are putting together in support of his Aether program. EUVPy contains a bunch of different EUV irradiance models that are used by the space weather community. And it's sort of the context for it is that we wanted to sort of let it be a one-stop shop for different irradiance models that are commonly used, so people didn't have to go to a bunch of different places to use them. They could just all use them in a single package. And we also will be introducing, as part of this package, a new irradiance model that Aaron and I have put together actually as well. So we'll start just with an overview of the contents. We'll discuss the context for EUV irradiance modeling in general, the need for this package, and then what the package is actually capable of. We'll discuss NUVAC, which is the new model that Aaron and I are putting together, and it's actually a part of this package as well, and path forward for further development for the EUVPy package. So for, sorry about that. For the context, pretty much all major ionosphere thermosphere models require estimates of solar EUV forcing. And since solar EUV itself is not observable through the atmosphere, it gets observed all the way down to about 90 kilometers in altitude. Most of these models use a proxy, which is usually F10.7 for the EUV. And F10.7 is the solar radio flux, really the flux density at about 10.7 centimeters. So it's in the radio. It's measured by Dominion Astronomical Observatory up in Canada, in the city of Penticton. And is also recorded by Nobayama Observatory in Japan. The proxy is pretty useful because of course it can be measured from the ground by solar radio telescopes. It's also very well correlated with EUV emissions as well. And it's important to note that a lot of the operational models in space weather, so these are models that are used by the space weather community for space situational awareness, for getting an idea of conditions under which radio communication and navigation will be affected. They use F10.7 for nowcasting and forecasting. And there have been a number of different papers that have been published within the last decade or so that have focused on forecasting the F10.7 solar proxy so that they can drive, so it can be used to drive atmospheric models to predict the ionosphere and atmospheric state in the future. There are some issues, though, with just relying on F10.7 alone that the community has talked about. And one of those things is that the emission sources or the emission generation mechanisms for F10.7 are just different in terms of the physics as regards to EUV. So there tend to be about two major sources, two categories of sources for F10.7 emission. And these are thermal Bremsstrahlung emissions and gyroresonance emissions, which are non-flaring sources, and flaring sources, which are gyrosynchrotron emissions. And really the major difference between these two types of emissions is that you get these non-flaring sources that are going to be more dominant during periods of solar quiescence. And they're really primarily caused by the motion of charged particles oscillating in magnetic fields. During flaring situations, those charged particles can exceed relativistic velocities where they're approaching a third of the speed of light. And so this causes what we call gyrosynchrotron emission, which also can be detected in the radio as well. But some of the issues that have been identified by the community with just relying on F10.7 is that F10.7 actually has a problem capturing actual solar minimum. There's a paper published in 2011 by Chen and authors that showed that F10.7 actually overestimates the contribution of solar energy to solar minimum and is not really able to capture the monitor minimum as well as it ought. And what you often see in F10.7 measurements is that they tend to kind of bottom out around 50 to 60 solar flux units. Rather than going lower than that, they're always registering some residual energy from the sun. That is a behavior that's not really seen in the EUV wavelengths. EUV itself is a complex quantity because it has a wide variety of sources. I mean, we're dealing here at energy that's released because of collisions between different particles in different parts of the atmosphere, and also thermal energy that ranges from, in about like 6 to 7 orders of magnitude all the way from the photosphere to the upper corona. And the wavelengths of light that correspond to those energy transitions and the energy that's being released by particles in all those different parts of the solar atmosphere are rather diverse, but they span the entire EUV spectrum. So using F10.7 as a single univariate time series to describe all solar activity is just going to be a little too coarse in terms of describing that dearth of information that the EUV actually captures. So here's like a kind of funny cartoon just to explain where like the emission sources are in terms of where the solar atmosphere, the regions of the solar atmosphere. So F10.7 is primarily emitted by the corona and the chromosphere, and as well as part of the transition region, whereas EUV is emitted in a whole bunch of different places with a whole bunch of different emission mechanisms, ranging from particle collisions in different parts of the atmosphere to emissions that are associated with solar flares, which can intensify all the way into the soft X-ray range. So we're dealing with a very, very diverse set of physical phenomena for which EUV emissions are actually released. And just to be even more drastic, the problem gets very, very, very complex when we start really getting finely detailed in terms of all the very, very different and unique solar processes that happen within the solar atmosphere. So there's granules, there's spicules, there's fibrils, there's magnetic reconnection happening in solar flares, and there's microflares and nanoflares that also are associated with EUV release as well. And these regions are all coupled with each other due to processes like Alfvén waves, MHD waves, magnetoacoustic waves, shocks, and magnetic reconnection. And all of those processes play a role in EUV emission. And really what I want to do here by highlighting all of this is just to say that what the community has agreed on is that really in the ideal situation, we want to be using EUV itself as the driver for any models of the ionosphere thermosphere. So in response to that need, empirical EUV models have been developed. And so there have been several over the years that the community has used. And some of the most prominent ones have been the HFG model. I want to apologize because the HFG is actually an acronym for the authors of the original model, and I actually forgot their names. So, but this model was released in the mid-2000s, and UVAC is another popular one that was released in the late 1990s. Was followed by HUVAC, which is a higher resolution version of that model. And what's similar between all of these models is that essentially what was done was that you had rocket measurements, or you had measurements taken by the Upper Atmospheric Research Satellite. And those measurements were basically, a model was basically a fit between F10.7 and often 81-day averaged F10.7. And usually these were linear models, fit between those two quantities and binned values of the solar radiance that were taken by these rocket measurements or by the Upper Atmospheric Research Satellite. And not all these models use the same type of linear parameterization. So for example, the UVAC model, which is very popular and still continues to be used actually today in a lot of publications, is basically a linear fit between a quantity called P, which is essentially like an average of the F10.7 and the 81-day average F10.7. So it's an average of an average almost. A linear model between those quantities and the rebinned solar radiance in about 37 different wavelength bins. Whereas the HFG model does something a little different. It's a little more complicated, but a lot of the parameters in the HFG model rely on understanding of photoionization cross-section rates. But there's also still the assumption of linearity between the coefficients of that model and the rebinned irradiance as well. There have been a number of other models that have been presented as well, and many of them use this approach of fitting between F10.7 and binned EUV measurements. So the Naval Research Laboratory has released 2 versions of its own EUV model. The last one, I believe, came out in the mid-2000s, which is NRL EUV2. The GHOST spacecraft, which is a multi-use Earth observation and space weather spacecraft, series of spacecrafts. The team that has developed the EUV instrument aboard that spacecraft also released an EUV model that basically fits between solar proxies and rebinned irradiance in I think it's like 18 to 20 different wavelength bins, all of different sizes. It's also important to mention that the HFG model doesn't have uniform bin width as well. It has 22 bins, and 5 of them are overlapping. So there's been a number of different models with different resolution and slightly different approaches for doing these fits, but most have been fairly linear. And there's also some limitations to each of these models. I think I discussed that a little bit in the next slide. Yes. So some of the limitations, or at least observations for some of these models, is that these models may capture the total EUV spectrum rather well, but they differ in terms of how strong that energy is distributed across different wavelength bands. So for some models, you may have a lot of the spectral power contained in the almost like the soft X-ray region. And then for a lot of other ones, you may have that energy distributed over different wavelengths, maybe between 400 to 600 angstroms or 800 to 1,000 angstroms. It differs depending on the model that's used. So although the total energy, if you were to just sum across all the bins in these models, and if you were to restrict the bins that you cared about to the same wavelength range to make sure they were corresponding between the models, you see that, generally speaking, the energy is fairly similar in terms of the total energy captured, but these models are kind of splitting up where that energy lives, and they're also splitting up how much variation there is depending on the bin that you're considering. So you'll see just in the plot here in a paper published by Judith Lean in 2003 that, for example, it's most drastic actually to see this in the wavelength ranges between 700 and 1,050 angstroms. You can see that the NRL EUV model has very little variation, and it tends to confine the variation of the energy within that bin range between about a half to about 1 milliwatts per meter squared. Whereas if you were to look at the Solar 2000 model at the very bottom, not only is like the baseline energy in that region a lot different, it's almost different by a factor of 2 or 3, but the variation is also larger, and it's confined between a different range, about 1.5 to 2.5 milliwatts per meter squared. So that shows you some of the results of the different ways that these models were parameterized, but we're also dealing with the effect of selection bias in terms of how some of these models were fit in the first place. So some of the models were primarily fit using data that happened during the declining phase of a solar cycle, or during the ascending phase, or during solar maximum, or during solar minimum. And so you're dealing now with the issue of generalizability. How well do these models that were fit using data from a specific part of the solar cycle actually able to capture variability in other parts of the solar cycle? And the answer is that it varies depending on the model, but there's limitations in each of these. So the community, noticing that these limitations exist, and yeah, this is just an extra slide to kind of show, sort of why some of these limitations are actually present. And part of that has to do with the fact that there have been different satellite missions that are taking measurements of the EUV at different times. Some of them have overlapped with each other, but some of these instruments are different. They differ in their degradation rates. They differ in terms of the wavelength bands that they cover. They differ in terms of the uncertainty and the measurements in each wavelength band. And so those are things that the community has to kind of deal with in terms of limitations and effects on any model that comes out of the resulting data that's used to fit here. So there's been a desire to kind of use all this data together in aggregate to develop the best model possible. And a very, very respectable attempt at that has been the flare irradiance spectrum model. And there's been 2 versions of this. I'm going to specifically talk about the second version today. But what's common between both versions is that the flare irradiance spectrum model basically combines measurements from the Solar Dynamic Observatory, the Source SOLSTICE spacecraft, the Upper Atmospheric Research Satellite, as well as, I believe, 5 or 6 different solar proxies, including the MG2 core-to-wing ratio, F10.7, and the Lyman alpha index, and kind of throws all those together to develop a model that covers between 0 and 190 nanometers at 0.1 nanometer resolution. And it basically describes the solar EUV flux in that range at high wavelength resolution. And what's really cool about it is it has a component that that accounts for variation in the EUV spectrum intensity due to the solar cycle and due to the solar rotation. And there's a flare component that also provides estimates of EUV at about 60-second resolution. So, and the cool thing about FISM2 also is that model results have been generated all the way back to 1947, which is where the F10.7 index first started to be recorded and made widely available. So this kind of represents a community standard, if you will, in terms of EUV measurements. And the great thing about it is that FISM2 has been started to be used by people who are doing a lot of upper atmospheric modeling. It's been used with the global atmospheric thermosphere model, which was developed by Aaron Ridley. It's been used also to develop models of the critical frequency of the F2 layer in the ionosphere, as well as the maximum density of the ionosphere in the F2 layer as well. And the performance of those models has been shown to be superior to just using F10.7 to try to predict those quantities. So it's already seeing widespread use within the community, and it's also seeing validation in terms of the paradigm that was used to make it, as shown by its success and improved results and improved modeling compared to previous approaches. There are still some concerns, though. The first is that there's no source code available, at least to my knowledge, at the time of my making this presentation for the FISM2 model itself. And also, there's not really an operational version. So it's important to note that to make an estimate of irradiance on the current day, to make an EUV spectrum estimate, FISM2 uses 108-day smooth values of proxies like F10.7 and Lyman alpha to generate that estimate. So in effect, it's requiring like data 54 days into the future to make an estimate of data at the present day. So that limits its ability for nowcasting and forecasting. And the FISM2 team is aware of this, and I actually assume that this is probably going to be addressed at some point. But they note in Chamberlain's paper in 2020 that because of this limitation, a lot of like the results from the last 2 solar rotations for FISM2 irradiance are essentially provisional. And so they use whatever data exists up until the present time to generate an estimate, but that estimate will not be as accurate as if there was, you know, future data available for any of the products that you were considering. So this combined with some of the difficulties of those different models I mentioned has motivated the development of the EUV Pi package that Aaron and I put together. So first of all, there really isn't a central place that we were aware of where all the open source EUV models like UVAC, HUVAC, and HFG can kind of just be used together in Python. And it's not always straightforward, at least to me, what those EUV models were doing and how they were used. I mean, I know just because of my own limitations as a scientist and my need for personal growth and continual development that I had trouble kind of understanding how the cross-sections worked in the HFG model and how the rebinning and the overlapping bins actually took place. You know, my initial assumption was that it was a simple sum between the overlapping bins that was just kind of divided into 3, and that you could do some sort of regression to figure out the proportion of energy that should be split across those overlapping bins. But it turned out that that proportion of energy is actually going to be dependent on the cross-sections, the photoionization cross-sections that are in that wavelength range. So it took me a little bit of time and being more annoying than I would have liked to some of the very generous co-authors on that paper to figure out how that worked. So it'd be great for students who are kind of being introduced to ITM modeling and solar and geomagnetic drivers of the solar terrestrial environment to just have a one-stop shop where they can understand how these models are being used and to just use them kind of right out of the box. And then also in terms of space weather operations, there really isn't a model as accurate as FISM2 that can be used for nowcasting or forecasting. So the space weather community is very, 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 very much indebted to the FISM2 team for its development. But it would be nice to extend that usability of FISM2 to an operational context that doesn't suffer from the need for future data to generate an estimate in the present. And one of the things that we noticed was that any such model that is capable of doing that in the spirit of well thought out and principled use of machine learning and uncertainty quantification should be flexible enough to provide for different binning procedures, since there's been different binning procedures that have been used by the community, such as those overlapping bins that were presented by the HFG model, as well as the 37 bins that have been used by the UVAC model. And the global ionosphere thermosphere model, for example, uses 59 bins, of which the 37 that I mentioned are a subset. Any model should be flexible enough to like jump back and forth between those different wavelength resolutions and wavelength binning procedures, but also should be able to provide quantified uncertainties so that you can get an idea of how much your downstream ionosphere thermosphere parameters are going to be affected by the inherent inaccuracy of that irradiance model. And this is particularly important since during quiet times, EUV is the dominant driver of the dynamics of the upper atmosphere, basically controlling 80%, governing 80% of the energy input into the upper atmosphere. So with all this in mind, EUV was kind of put together as a way to address these needs. So what are the capabilities of the EUV Pi package? There are 4 principally. So the EUV Pi package contains 4 different empirical solar EUV models, and these have all generally been the ones that are most accessible by the community and are most widespread in use by the community. So the first is the UVAC model that was developed by Phil Richards in the late 1990s. It also includes a version of the HUVAC model, which is the high-resolution version of the UVAC model. And that was developed by Phil Richards also in the early 2000s. It includes the HFG model, which was originally released by Solomon and Kyan. And it also contains the NUVAC model, which we'll talk about a little bit later. And that's the model that we developed in response to this need to have FISM2 irradiance values on an operational basis. So EUV Pi makes running these models in Python easy, and it provides tools for generating irradiances for direct ingestion in the global IT models. And I'll talk about that last point with an example that we'll get to in the future. So we'll go over a few examples here. The first is individual spectra. I apologize for how small the code on here looks, but pretty much everything after after this line is just plotting. So it's pretty simple to just provide the EUV software with just like some sample values for F10.7, 81-day averaged F10.7, and that quantity F10.7b is 54-day averaged F10.7 in a backwards looking window, and I'll return to why that's an important quantity later. But if you have those values, you can basically just load in info about the wavelength bands that you care about, which is done here in these lines. And then after you have that information, and this is really just used for plotting, you can generate some irradiances just by passing in those values that you defined above or obtained from somewhere like OmniWeb or a website that, or like, you know, the Canadian Space Agency's website that provides F10.7 values. You just throw those in as arguments to whatever model that you're trying to generate irradiances for. So it could be NUVAC, which is here, and it could be UVAC here, or it could be the high resolution version of UVAC here. Oops. And then you'll immediately get out estimates of what the irradiance is going to be from those models. You'll also get an estimate, or you'll not an estimate, but you'll get the wavelengths that those irradiances correspond to, and you can just plot them like so. And that's what we kind of see here. We see here the irradiance for NUVAC, UVAC, and the high resolution version of UVAC, all between 0 and just above 1,000. So I think it's 1,050 angstroms. And this is displayed in the log scale. And this is the binning scheme that is used by native UVAC. So it's those 37 bins that have been used since the 1990s. They're all about 50 angstroms wide. It's 5 nanometer wide resolution. But you're not restricted to that binning scheme. We can also use what's called the Solomon bins, which are those 22 variable width wavelength bins, 5 of which are overlapping, and that's displayed here. And I want to note in this display that the irradiance in the overlapping bins is just all summed together for simplicity and for visual aid. These bins are also called the standard bands, and so you'll see that on like the University of Colorado Boulder's website, where they have a bunch of different irradiance data in their last interactive solar radiance data center. They have data in the standard bands for a bunch for the FISM2 estimates, for example. But you can generate irradiance in these bands as well, just very simply by telling whatever model that you decide to execute what bands that you want. So you can tell it UVAC, or you can tell it standard bands, or Solomon is usually the argument that you'll see in the package itself to generate irradiances in those bands. You can also generate simple time series, which is nice if you just want to see how the irradiance in a given band is varying over time. And what's cool here, I also want to mention, this example is kind of perfect for it, is that EUV also contains functionality for just immediately downloading F10.7 data without having to like make your own web scraper to do that. And so you can just give it dates, and it will return Earth-Sun distance adjusted flare corrected F10.7 data. That's actually on the Collect Localization Satellites website. That's a part of the French Space Agency, and they host that data. You can also tell it whether or not you want to truncate the data. So for example, if you're looking at more than 3 solar rotations of F10.7 data, and that data includes data up to the present time, you can tell it to truncate it, which will, I believe that what that does is it cuts off some of the data in the past, leading up to the date that you chose. And the only reason it does that is because it's computing averaged values. And so there actually won't be average values to like, there won't be values to calculate something like the 81-day centered average. And so what it will do is it will cut off as many values as possible, or as few values as possible, to allow you to still get those average quantities. But it will only use the data that is possible to use to create those average quantities. But as a result of just running that function, you'll get a list of date times, which are basically F10.7 values are associated with noon and universal coordinated time. And then you'll get F10.7 itself, 81-day averaged F10.7 centered on the current day, and then 54-day averaged F10.7 in a backwards looking window. And then from that, you can run just like before, any irradiance model that you choose that's available within the EUV package. So here we're running NUVAC, that new model that we'll be talking about in just a second, as well as UVAC. And we're just plotting the irradiance in the 10th wavelength band, which happens to be centered at 375 angstroms. And so you can see here the UVAC results in green and the NUVAC results in orange. And this is over the entirety of solar cycle 24 that we're showing here. So there's more that you can do with the time series as well. And this is primarily for just the purposes of visualization, so we can get an idea of the difference of these models and how that shows up in the EUV-Pi package. But we're also capable of showing the total irradiance in the UVAC bins and in the Solomon bins all summed together across, so we can look at total energy that's captured by each of these models. And that's as simple as running the models like I discussed before, but simply just after you're done doing that, summing across the last axes to basically add all the irradiances together to get an idea of what the energy scaling looks like for everything. So this is just another example of the fact that you can do that both in the UVAC bins. Those are those 37 bins that are all spaced by 5 nanometers, and the Solomon bins as well here as well. And you can do that for different models. And I'm also showing here the HFG model, which I didn't show in the previous slide, on the right-hand side as one of the models that you can also use as well. And the last thing, which will be a good segue into one of the cooler parts of the package, is that there are ways to run our new irradiance model in terms of an ensemble. So, and I guess I might actually wait until discussing this a little bit later, but I want to preface by saying that our new irradiance model benefits from the fact that it, one, provides uncertainty quantification estimates, and two, the way in which it does that allows you to repeatedly run the model over and over and over again in a sort of Monte Carlo fashion to get an ensemble average of what the irradiance is going to be. And then from that ensemble average, you can basically get an idea of the confidence bounds of the model and also get an idea of what the most likely estimate of the irradiance is going to be in a particular band. And that's a capability that is unique to the NUVAC model itself. And with that capability identified, leads me into discussing NUVAC. So NUVAC is primarily at a very, very top level. FISM2 Lite is what I call it, with uncertainty quantification. So like I prefaced to the beginning of this presentation, NUVAC was developed with the desire to obtain irradiances that were on par with accuracy and statistical characteristics as the FISM2 model, but in a way that did not require estimates in the future of proxies to generate. So it would be suitable for nowcasting and forecasting. And how we did that was basically we have a nonlinear fitting paradigm where we want to use as our model driver something that is widely available to the space weather community and everyone is familiar with. And so we chose F10.7. And here's where that F10.7 averaged over 54 days in a backwards looking window comes into play. So that's a quantity F10.7b that you see here. And the reason why we also include that as a model driver is because if we're doing nowcasting and forecasting, we only want to have to rely on data that we have now or in the past. And so by restricting our model fitting to that, we basically set our model up to be applicable for nowcasting and forecasting in a straightforward way. And so we have this nonlinear fit here where the irradiance in a given bin I is some linear combination of F10.7 and F10.7b, where these two arguments are raised to a power that is found via linear regression. And we have also a term here that takes the difference between those two values almost as a way of showing that we're also including a contribution to the departure from the daily F10.7 away from some baseline that's represented by this 54-day average, which you can think of that as the bulk solar activity over the last 2 solar rotations. And so we're including some functional dependence on the modulation away from that average solar activity as well. So this paradigm allows for increased flexibility in modeling the statistical characteristics of the irradiance in each bin. I'll show you some pictures of that in a minute. And it does that in a superior way than just the linear fit, which will essentially limit, especially during active periods, how much of almost like the heteroscedasticity, so the tendency for the variance to change over time in the data is going to be better represented by a nonlinear parameterization like this. In the uncertainty quantification itself, I think I'll wait to talk about that until, I believe I talk about that in the next slide here. Yes, sorry about that. So I'll get to that in a second, but I want to highlight first how useful the nonlinearity is in improving the statistical representation. So on the left-hand side here, we have solar irradiance in 6 different bins as a function of that quantity P that I talked about before, which is basically just the sum of F10.7 and 81-day average to F10.7 and the average of those two things. And what you can see here is that the NUVAC estimates are in orange and the FISM2 measurements are in blue. And there's an increased width that shows like the better variance that's being captured by the NUVAC model in each of these different wavelength ranges. It's not the same, obviously, in each wavelength range. I mean, and the top row is showing some wavelengths that were selected from the Solomon bin, sorry, not Solomon bins, the UVAC bins. And the bottom is showing some wavelengths that were selected from the Solomon bins. And you can see here that the ability to capture variance in the Solomon bins in particular is better in the middle of the wavelength ranges for those bins than it is at the edges, particularly at the longer wavelengths. But nonetheless, not shown, but nonetheless, when you compare these results to those for UVAC and HFG, you basically just see that UVAC is a straight line, kind of like cutting up through the middle of the FISM2 estimates. And you see that HFG is actually spread out a lot, but the amount of spreading is different depending on the wavelength range. And what you also see is that with HFG in particular, the slope deviates significantly from what the FISM2 estimates are showing. I will concede that this analysis is assuming the correctness of the FISM2 approach, and the reason that we're comfortable making that assumption is because of all the data that was used to make that model, which is why we're using that as the thing to fit to. But nonetheless, this nonlinear parameterization is demonstrating itself to be a much more flexible approach than just the linear approach that has been done previously in the literature. What's nice also is that it proves to be generalizable. So, and that's part of the reason for that is just that the domain of data that we are working with spans 4.5 to 5 solar cycles worth. And so you're going to get a better representation and capture of different solar conditions just by virtue of fitting data over such a larger domain. But also the nonlinear parameterization itself allows the variation inherent in that choice of domain to become more apparent in the resulting model outputs. And that's kind of being shown here on the right-hand side. We see solar spectra during low activity here on the left of this plot. And then we see the corresponding solar spectra during high solar activity on the right-hand side. The FISM2 values of truth are in blue in both. And then the NUVAC ensemble average of 100 ensembles is overlaid in orange with error bars that are also present. If you can see that, I apologize if this is a little small. You can see the error bars are a little different in how large they are depending on the wavelength that is chosen. But nonetheless, the ensemble average is spot on with the FISM2 estimates, which is pleasing to see. And we also see that accuracy for NUVAC is essentially identical depending on the solar condition. So we're not really seeing a major deviation of NUVAC away from FISM2 just because it's solar minimum or just because it's solar maximum. So that also is a good confirmation of the generalizability of the approach. So uncertainty quantification is a fun part of NUVAC that I want to highlight. So the thought behind this process was that essentially when we do our initial fit between our nonlinear model for NUVAC and F10.7 and 54-day average F10.7, if you just take a difference between the NUVAC estimates and the FISM2 values, you'll get a bunch of residuals across all the different bins that you consider. And the question is like, how can we use those residuals wisely to get an estimate of how uncertain irradiance estimates are in each bin when we just run the model in the future? We have new estimates of F10.7 and F10.7b. The thing we noticed for this is that we didn't want to just do something as simple as plotting out the residuals in each bin as a function of F10.7 and then assuming that there was some sort of linear relationship there that you could capture, because we noticed that the residuals are in each bin are actually correlated with each other. And so if you're going to generate an estimate of uncertainty, that estimate should incorporate that correlation. And so what we did was we made these normalized covariance matrices between the residuals in each bin. And then what we did was anytime an ensemble was generated, we used this covariance matrix to essentially perturb the estimate of irradiance in a given bin to an amount that is dependent on that covariance, the value of the covariance matrix for that particular wavelength range. And the idea is that the amount of that perturbation should happen with respect to a neighboring wavelength range that is well correlated with the one that you're trying to get an estimate for. So we're trying to leverage that correlation to get a more accurate and faithful representation of what the uncertainty is going to be in each wavelength bin. So this is essentially an idea of like saying that because the errors are correlated, we can use covariances to provide an estimate of the joint posterior distribution over repeated sampling of our irradiance. And eventually what you'll get is you'll get an ensemble of irradiances for which the distribution of errors in that bin is going to approach the original distribution of the residuals for which you actually generated the covariance matrix itself. And this is kind of shown here on the right-hand side where the covariance matrix itself is on the left. But in the middle up here, we see the percent deviation between the NUVAC irradiance estimates and FISM2 irradiances at a bin centered at 425 angstroms. We see that the mean is very, very close to 0. And then this is, this black line is basically an estimate of the error distribution, which was found with kernel density estimation. And then the standard deviation of that distribution is shown with the sigma value here. And then the result of this is that you can show the repeated random sampling to get an idea of how much the wavelength really should vary in terms of your uncertainty in that particular bin. And that's being shown here on the right in the bottom, where the orange, it's kind of hard to see, but there's a solid orange line that represents the ensemble mean. And that's fairly close to the FISM2 estimates the entire time. But we're also seeing that this shaded region, this shaded orange, is the result of the upper and lower bounds of that ensemble from repeated random sampling of the irradiance estimates for this particular bin. And the nice thing about it is that for the vast majority of the time considered here, and this is only the beginning of solar cycle 25 that I'm showing, the FISM2 true values are falling within or close to the expected range of the output for the NUVAC model. So what remains? What are our paths forward? So the first is that we want to get an idea of how best to set the lookback window. Setting it at 54 days is reasonable in terms of wanting to include information from the last 2 solar cycles, but there's probably some either optimal value of a look-back window to use as one of our model drivers, and that's something that we'd like to explore into the future. Or it's possible that the size of the look-back window might vary as a function of solar activity or other conditions that are worth considering. So some sort of dynamic description of the look-back window for F10.7b is worth looking into in order to increase accuracy of the model. And also, one of the things that we noticed in terms of irradiance in each wavelength bin is that for different wavelength binning schemes, you'll have irradiance that you're estimating like between value A and value B, and there's some delta in the middle that's maybe like 1 nanometer in width, or maybe like 5 nanometers in width. But there are also individual wavelength lines that correspond to specific atomic transitions that are important in terms of describing impact on the ITM system. And we had to handle those differently. Essentially, what we did as a first cut is we found the index associated with that particular wavelength line, and then we basically made the judgment call that we wanted to consider as part of the emission of that wavelength line any irradiance that's 4 nanometers to either side of it, and we sum those together, and then say that irradiance, the energy in that wavelength range, corresponds to the wavelength line. Now, it's not exactly clear to us whether or not that's entirely justifiable. We know that in lower resolution satellite measurements, such as times C, because everything has been binned up into 5 nanometer wavelength resolution, there's actually just going to be what they call blends, line blends that show up in contributing to some of the energy in those bins, because those bins are overlapping very, very strong wavelength lines. And so the energy is just arbitrarily summed into the bin. But we don't know for specific wavelength lines that we wanted to consider in our model, such as like the UVAC bins can contain at least 5 different prominent wavelength lines, how we ought to treat rebinning irradiance into those specific lines. So that's something that we are still going to be exploring. We also want to stress test the NUVAC model itself by doing some ensemble runs with GITM. So now that the EUV Pi package is capable of just like spitting out NUVAC estimates in a text file that you can just tell GITM to use, we want to do some ensemble runs with it to see how much uncertainty in the NUVAC estimates actually affects uncertainty in downstream ionosphere thermosphere parameters in a model like GITM. And then there's the additional work we'd like to do making available in Python some of the heritage and legacy code that's been widely used in the atmospheric community. And so some of that include the rebinning code that Liang Qian actually used when she was developing the HFG model and making that available to people, as well as the photoionization cross sections, making those available and including along with it some technical documents that will make it very easy for graduate students or people who are making a transition to working more with EUV stuff to understand how they work and how they're used to do the rebinning. And then in the future, something that we may explore, and which was actually recommended to us, was that we may think about an entirely novel or like rather radical extension of NUVAC, in which we are doing from the ground up some assimilative nonlinear modeling of EUV that is based off of different solar proxies. So F10.7 is one option, but there are other ones, such as the energy of EUV that's summed across an entire range. This has been done with the FISM-M model that was recently released for use at Mars. And so there's a way to think about trying to extend the NUVAC approach to using different solar drivers or solar proxies or estimates of solar radiance to try to reconstruct what the entire UV spectrum would be. So it'd be really interesting to see like which proxies work best, which look back window works best, combine those two together and figure out which paradigm could be used for having the most accurate estimates of EUV across the entire spectrum, and then trying to extend that to use throughout the solar system. So are there, I mean, I would assume, perhaps without rigorous justification, that certain paradigms are going to be more applicable to the area around 1AU, where there'll be others that are more applicable to around Mars or Venus. So it'd be interesting to try to extend this paradigm in a way that is applicable to just doing space physics throughout the entire solar system in general. And then in the future, something that I think is specifically on my mind is to make some sort of operational NUVAC portal. I'm not sure I have to think about whether I want to make this as part of a future release of NUVAC on the current GitHub page. But it'd be cool to just kind of like regularly develop ensemble estimates of future irradiance 1 to 3 days ahead with different forecasting techniques, maybe do some ensemble averaging, like have one approach that uses a neural network to do it, maybe use another approach that uses some sort of autoregressive integrated moving average, or maybe some other approach that uses something like a vision transformer to train on synoptic maps from the gong magnetograms to estimate what solar radiance is going to be, and then kind of combines those all together in a central place to provide operational estimates of the EUV spectrum for the space weather community just in general. And it'd be great if that was all in Python as well. And so people are having some sort of like operational Pythonic EUV forecasting environment that the space weather community can use at will. So with that, I want to wrap up just by saying thank you. First, I want to thank my co-author Aaron Ridley for really like being the brains behind this research, and to setting up this paradigm and supporting the development of the package. I want to thank a number of other colleagues and scientists. Carl Henney and Piyush Mehta, I was able to have a lot of really useful conversations with EUV forecasting and understanding some of the science questions involved and in this area at a very fundamental level. Eric Vega, I've worked with him at Michigan Tech Research Institute for a few years now, and through him I've have a lot deeper understanding of uncertainty quantification and statistics. I've also had some conversations with Sam Schoenfeld, Bill Peterson, and Phil Richards, who I'm very grateful for making the HUVAC code available to be ingested as part of the EUV package. And I'm very comfortable in saying that none of the developments of EUV Pi really would have been possible without input from all these people in conversations or in hard science or otherwise. So I'm very grateful to them. They've helped to make EUV Pi possible. And with that, I will close and see if there are any questions. So, thank you very much.
Reactions are always hard to find whenever I want to have them, but thank you. Do we have any questions for Dan?
I wanted to ask real quickly, this seems like an obvious thing, but you were presenting your new package here, and you do plan to submit this as a PyHC package at some point, right?
Yes, that's the aim.
Wonderful. I welcome that, and I'm looking forward to seeing that PR come through. I'd be happy to have this under our umbrella.
Thank you so much.
And yeah, not a question, but also just a comment. Thank you for including all of the background you did, especially the comparison with the F-17 stuff, because that was informative for me, actually. I was able to follow this, and it was pretty technical. And usually would kind of go over my head, this kind of stuff, but you did a good job of making it understandable for me.
I appreciate that. Yeah, I was actually worried the whole time because I felt like I was monologuing. So I was like, man, I hope I'm not losing people. But I'm glad that people felt that it was understandable.
Yeah.
Sure.
And here I see a hand up, so I'll step aside for a second.
Yes, please go ahead, Jeff.
Hey, Dan, this is really great stuff. I'm happy to see a lot of more movement on this and pulling these different models into Python. I was curious about the binning procedures and if the plan moving forward for EUV Pi is to just subdivide into all of the different binning things that are used by the models, or if there will also be some form of integration. So you're looking at kind of the average power delivered to monotonic oxygen or O2 or things like that. Because that's something we've discussed as possibly being a useful proxy for looking at direct solar input when we're actually comparing on the data side to EUV forcing.
So I can speak to the first one a little easier. There's interest in just like, at least from me, for including the ability to just like arbitrarily rebin things. I want to do that in a principled way. I remember I talked a little bit about some of the difficulties with the wavelength lines that we've encountered. I'm not super aware actually of some of the stuff that you mentioned with the atomic oxygen. That sounds super interesting. So I'd be happy to be emailed and educated on that, because it sounds like a capability that's definitely worth including.
Yeah, I'll follow up with you on that.
Yeah, I think that what we would do is basically make a database of cross sections, and then you just basically have to multiply the wavelength bins, or the flux in the wavelength bins, times the cross sections to give you some sort of an integration of how much is being absorbed by different constituents. So it should be straightforward to do, but we definitely have not thought of doing that at this point.
Awesome. Do we have any further questions? Comments?
Yeah, I kind of want to ask again real quick, not to steal the floor too much, but obviously you're bringing in some different models here in this package. Are all of them just pure Python implementation, or with any of them are you like wrapping another language like Fortran or something to get the functionality?
Yes, a good point. So HFG and UVAC are just straight Python, but the HUVAC model, which is like the high resolution version of UVAC, is actually written in IDL, and so that had to be Python wrapped.
Okay, so you got a Python wrapper around IDL there, and then Python for the rest of it purely.
Yep.
Nice. I usually like to apologize to people on behalf of LASP for IDL, because the lab I work at invented that language. So if that was a problem for you, whoops, we kind of did that.
I'm not gonna lie, I had some griping moments when I was trying to figure that out, but I got some great colleagues here who are some hardcore coders, and they helped me out with that one. So
And well, we really only have time for like one more question. We're at the top of the hour. Anyone had a short thing they wanted to throw in there?
It sounds like no. Well,
Yep.
Dan's
Telecon, 15 seconds.
Dan's email was CC'd along with this. If you have any more questions for him, feel free to reach out. And we will have another biweekly telecon in 2 weeks' time, so September 23rd. And we're going to be talking about some of the various FEPs that we have up right now, just reminding people, that they're there, and you can always go comment on them. And then I know John Niehoff submitted a few different GitHub issues related to potentially some standards related FEPs coming down the pipeline. So be sure to check those out, and we'll see you again in 2 weeks' time. And thank you again, Dan.
thank you for having me.